In the next few minutes, we will present the application of our energy optimization tools, which are based on some discrete event simulation models and integrated energy analysis and optimization. As you may have seen in our introductory video, we referred to two use cases, of which the first relates to the Arcelic washing machine plant, where we made use of Siemens Technomatic plant simulation in order to forecast the production output and the energy consumption based on several input data. To provide you a quick overview on the model, we would just like to highlight that it is composed by several production lines and assembly lines, and as it is indicated right here, there are several 3D models or templates used in order to represent the overall facility. You can also see the actual model as it is implemented, and we would just like to highlight that in this case it is not relevant that there are very precise and pretty visualizations. It is just necessary to have the right references and to have the correct underlying layout, so to represent transport speed and production times in an appropriate manner. So we made use of the available 2D layouts and tried to implement all the models and modules that are necessary to investigate the production system behavior. To provide you a better understanding of the overall model, I would just like to explain the most relevant parts of the so-called energy module. The energy module is composed by a user panel, some network panel, and also all the required sources, storages, and the energy distribution center. So it updates and records the energy demand of the production status and the material number. That means the model and input data of the simulation model. It then simulates all the different amounts of energy provided by local sources or also provided by the grid, and different types of storages and the overall system also related to the external interfaces is provided. To provide you some hands-on insights, we will have a look at the simulation model itself, and the simulation run starts with an interface provided by one team. You can update and upload some required input data, but there are also default values available. By generating this GUID, which is transferred to our simulation model, we can then follow the process of our simulation. I will speed up this a bit since the calculation takes and requires quite some time, as you see down on the right side. But as soon as simulation has finished, we receive some results related to the same GUID and can then switch back to our user interface, which is accessible via the web browser. So results are transferred and the visualizations are also provided, which means that we generate some production output throughout 1 week as it was provided by the input data, and we see the power consumption along the production line in the same time horizon. The second use case, as already mentioned, relates to the Tofaş production facilities, where we combined simulation with some integrated optimization in order to optimize the startup times of different production facilities. The E-code line comprises two distinct paint lines, the Eisenmann line and so-called JICO line for different models. Upon the arrival of the body shop, the car body is immersed in a paint tool to apply the coating and then undergoes heating in the oven. Each line contains a pool and two parallel identical ovens. After exiting the oven, the cars from the Eisenmann and Jaiko lines converge and proceed to the common sealing line, since the structure of both lines is similar. So, there are two important car body reserve areas which have an impact on the line startup time. The first area is located short after entering the Eisenmann line, which is reserve area 1, while the second area is before exiting the line, reserve area 3. The pool and oven must be preheated to a specific temperature before production, and the duration of heating varies depending on the facility temperature and ambient temperature. To ensure an appropriate start and stable performance of the subsequent sealing, it is crucial to preheat the pool and oven in a timely manner. However, maintaining the oven and tool temperatures consumes a significant amount of energy, which can result in energy loss if very early preheating is conducted. The underlying optimization method is a genetic algorithm, which requires some input like the initial number of cars, the energy demands and heat up times, and also the line productivities. This is represented in one large chromosome, and then by applying the typical optimization operators, the parameters are set, calculated, and evaluated. By getting a fitness value and comparing this throughout several iterations, the best fitness value, and that means the best parameter configuration, is selected, which results then in the appropriate startup times. As with the first case, we also provide an overview on the interaction with our simulation model. So you see the same interface provided by one team. In this case, you can also enter some input values, and then you start the simulation run, which results in a GUID and the transfer of these input data. Based on that GUID, which we see right here, you can then see the optimization process started at the Siemens Technomatic plant simulation module. I will also speed up the process in that case to give a quick insight into the results. So at the end, the fitness model and fitness value is generated, and by refreshing the user interface on our web interface, we generate the startup times that are now provided to the production managers and production planners to adjust the startup of each oven and pool. So that was a quick insight into our energy optimization tools, and related to this, just a short comment and disclaimer: there are still some minor adjustments and optimizations ongoing, which may result in some small changes in the interface and also the provided output data by the models. But in general, we hope that you got an overview on the tools and the underlying simulation models. And if there are any questions, feel free to let us know.